All right, guys, so welcome to this video. Here we finished up Chapter 5 completely, and the purpose of this video is twofold. First, we'll be covering the main learning objectives from Chapter 5 and tying everything together, talking about what you need to know about polynomials for the final exam. And then at the end of the video, we will have a short quiz. And unlike the other quizzes that have been in Blackboard on previous days, we will have the quiz at the end of the video. You'll write out your supporting work and then submit that supporting work in the module. Okay, so again, we're here in Chapter 5, and it's all about polynomials. Okay, so there were 7 main sections throughout this particular chapter, and the first one that we talked about was section 5.1, and that was all about parabolas and quadratics, right? So just as a quick reminder here, a quadratic function is something of the form f of x is equal to ax squared plus bx plus c. And we talked about sort of the details of these sorts of polynomials. And remember, this is degree 2 polynomial. So degree 2 polynomials we call quadratics, and the graphs of them are called parabolas. So we should be able to look at those characteristics of a parabola. For example, the vertex is one of the main characteristics of the parabola that we were interested in. We should be able to understand how the graph of a parabola is related to the quadratic function. So in other words, this formula here, right? So remember, you can pick out the x value of the vertex by taking negative b over 2a, and you can then figure out the y value of the vertex by evaluating f at that particular value of x. And then based on the value of a, if it's positive or negative, that'll tell you if the parabola is sort of opening upward or opening downward. And that will allow you to determine sort of the long-term behavior of these parabolas, and also where the minimum or possibly maximum value occurs. And it always occurs on the vertex. So we saw a lot of examples in the homework where we were looking at applications, and in those applications you had to minimize or maximize something, and you did that by finding the x and the y value of the vertex. And that's what's meant by this last one here on solving problems involving the min or the max of a quadratic. Okay, so again, this is just looking at the vertex. That's the main characteristic of the parabola that we were looking at. And then sort of just mainly understanding those formulas for the vertex. Okay, so that was that was section 5.1. And after we did 5.1, we said, okay, we want to do sort of the same setup, but now for higher degree polynomials. And we were really interested in what was called the end behavior of our functions. And we saw that the end behavior was dictated by what are called power functions. Power functions are just polynomials that have one term, right? Like something like a times x to the n. And we sort of analyzed the sort of end behavior of those particular power functions, and we saw that the end behavior basically just depended on whether or not the degree of the polynomial was even or odd, right? If it was even, the two endpoints were sort of going up or going down based on the leading coefficient. And then in the case that it was odd, it looked like one of these x cubed sort of functions that had this sort of shape to it. So one side would be going up to infinity and the other would be going down to negative infinity. And again, the reason why we talked about these power functions was because when the value of x got really large, polynomial functions behave basically the same as a power function. And so to determine the long-term behavior of a polynomial function, we sort of look to the leading coefficient of the polynomial, see that it's a power function, and then base our observations on that. Now, when you zoom into the origin, sort of close around the place where the x and the y-axis intersect, there can be all kinds of strange behavior. And that's where we started talking a little bit more about zeros and multiplicity and that sort of thing. But yeah, all of this information here is given to you by the degree and the leading coefficient of the polynomial. And then one other thing that we introduced at that point is some of the arrow notation about sort of looking at what happens as x approaches a number from the left or from the right. So just as a quick reminder here, if I write down something like x approaches 3, there's two possible ways that x can approach 3. It can approach it from the right, from larger numbers, or it could approach it from the left, from smaller numbers. And you indicate that approach either from the left or from the right by putting a subscript up here. Negative means from the left, positive means from the right. Okay, so we should be familiar with how to sort of express this long-term behavior in terms of these arrow notation. And we also did that when we started looking at rational functions, and we were looking at horizontal and vertical asymptotes, same sort of notation. And just as a reminder, we really do need this notation. It's not just like we're asking you to learn something that is not necessary. And it's because a lot of the times you'll be approaching values that are not in the domain of the actual function. So you can't put any sort of equal signs, and you can't even plug them into the function. Okay, so that was 5.1 and 5.2. Again, parabolas, and then sort of building up the end behavior polynomials and sort of seeing what the leading coefficient and the degree can tell us. And then we started to move on to sort of the behavior, not in the long run, so what happens when x gets really big or really small, but the behavior sort of around the origin, right? When you look at sort of smaller values of x. And in that case, we should recognize sort of the main characteristics of a polynomial function. And I would say those are the turning points. Sort of in a parabola, the analogous thing would be the vertex. The zeros or the x-intercepts. Remember, the zeros just tell you the locations of the places where the graph passes through the x-axis, and the x-intercept is an ordered pair. And then you also have the y-intercept as well. So these were sort of the main pieces of a polynomial function. And one of the things that we had a lot of practice with in the homework assignments was using the idea of factoring to solve for the zeros of a polynomial, or in other words, to find the x-intercepts. And the reason that worked out for us is that, you know, if you multiply two numbers together, let's say a and b, and they end up being equal to 0, then it's either a that's 0 or b that's 0, right? And that's because if both a and b weren't 0, then when you multiply them together, you wouldn't get 0 either, okay? So this idea of using factoring to find the zeros is based off of this property. This has a name, it goes by the zero factor property. But the idea would be we want to factor the polynomial as much as we possibly can, and then set each of those remaining factors equal to 0. The factors should be easier or sort of simpler expressions, and so you should be able to solve them more easily. Okay, so that's how we were using factoring to find zeros. And then remember, in later sections, we sort of reversed that around, right? We were finding zeros in order to help us factor the polynomial. So it's sort of a two-way street here. You can go back and forth. But as we started to really look at factoring and looked at things very carefully, we realized that when we were identifying zeros, there were two very different types of zeros, and it was related to what's called the multiplicity. So there are two ways to think about the multiplicity of a polynomial. One is in terms of the equation, and the other is in terms of the graph. So you might have the graph of a polynomial here that looks like something like this, and it just sort of goes on forever in both directions. But you'll notice that sort of the zeros are here, here, and here, and also over here. And you can determine the multiplicities if they're even or odd based on whether or not the zero passes through the x-axis or bounces off the x-axis. So you'll notice that this is bouncing off the x-axis, this is bouncing off the x-axis, and this is bouncing off the x-axis. And therefore, each of these three zeros would have an odd multiplicity. Most likely they'd be multiplicity 1 because they look linear when you're going through the x-axis. But for sure, we know that they are odd multiplicities just because they're passing through the axis. And then if you have a zero that looks like this, that hits the x-axis and bounces back basically off it, then we saw that that meant that you had an even multiplicity. And you could also determine this sort of thing directly from the formulas. So for example, if you had a polynomial of this form, then this polynomial would have two different zeros. There'd be a 0 at x equals -2, and there'd be a 0 at x equals 1. And you would be able to figure that out by setting these two factors equal to 0. However, you'll notice that this x plus 2 has an exponent of a 2, and so we would say the multiplicity here is 2, and this one has an exponent of a 1, so we say the multiplicity is 1. Okay, so that's this idea of multiplicity. You can get it both from the graph itself and also right from the formula. The formula is a little more precise because it will tell you the actual multiplicity itself. The graph is only going to really tell you if the multiplicity is even or odd. Okay, and just like we were saying in the last sort of section, we can determine the end behavior of a polynomial just by simply looking to its leading coefficient, right? In other words, we look at that leading term, leading coefficient, and the degree, and the behavior of the polynomial matches the behavior of the power function. And we just sort of talked about the shape of those power functions. And then just as a reminder, the end behavior is best expressed in terms of arrow notation. So you'll need to know how to talk about arrow notation. We should understand the relationship between the number of what are called turning points and the degree of the polynomial. And what we said is that the number of turning points for a degree n polynomial can be at most n minus 1. Okay? So for example, if you're dealing with a parabola or a quadratic as degree 2, and so it can have at most one turning point, right? And that would be right at the vertex. So there were a lot of questions in the homework that were asking you, here's the graph of some function, determine the smallest possible degree of a polynomial that has that function as its graph. And all you did was count the number of turning points and add one to it, okay? So turning points were sort of telling us about the degree, and there's this really interesting relationship between the number of turning points and the degree. And again, we derive that sort of relationship by thinking about if you take a degree n polynomial, you can only sort of factor it into n different pieces, right? And so when you do that factoring, you'll only have n zeros at most, and in between every zero you have a turning point. So that's why there's one less. And then we took a whole day to really focus in on what we were calling polynomial long division. So you should be hopefully really familiar with this algorithm by now, and you've done lots of homework problems where you've sort of divided one polynomial by another. And you go through this whole process, and you should be familiar with the terms, right? So remember, there was dividend, divisor. The dividend was the thing on the top of the fraction. The divisor was the thing you're dividing by. And then your quotient was the answer that you sort of got on the top of the long division, and then the remainder was that thing that you got at the very bottom. And the beautiful thing was that if we found that the remainder was 0, then the divisor was actually a factor of the original polynomial. Okay, so for the final exam, you should be really familiar with this division algorithm, this long division algorithm for polynomials. It will certainly come up. And again, it'll also help you find the zeros of a polynomial, and we saw that in later sections. Okay, so the main theorems that we had sort of relating factoring and zeros were in 5.5. The first one was what we were calling the remainder theorem, right? And the remainder theorem was just telling us that if I take some polynomial, let's call it f of x. So if I take some polynomial f of x and I divide it by a factor like x minus c, then after I go through this whole process, I'll get a quotient up here, some answer, and I'll get a remainder. And it turns out that we showed that the remainder has to be f evaluated at c. And this is only when you're dividing by something like x minus c, where c is a constant. So for example, if I divided by x minus 2, the remainder would be f of 2. And this is, again, a two-way street, right? If you compute just from the formula f of c, you'll know what the remainder is. Or you could go through and do the long division, find the remainder, and you'll have computed f of c. So you can sort of do this in both directions. So that was the remainder theorem. And then we saw the factor theorem. The factor theorem just said, okay, well, if you have a 0, right, if f of c is equal to 0, the remainder is 0, and then x minus c was a factor. And we used this information when we could sort of guess a 0, right? If we had some really big polynomial, we could figure out maybe 1 was a 0 or 2 was a 0. We plug it into that thing, and then we realize, okay, well then, you know, x minus 1 or x minus whatever the 0 was, it's going to be a factor, so we could go through long division, get the quotient that comes up here, and multiply x minus c times that quotient to get back our f of x, right? So the factor theorem told us that if we have a 0, then we have a factor, right? So if there's a 0 at c, then there's a factor of the form x minus c. And this is what I was saying, sort of going in reverse as well, right? So in the previous sections, we saw that if we wanted to find the zeros of a polynomial, we could factor it, set the factors equal to 0. And this is sort of the exact opposite of that, right? If we find a 0, we can then use the fact that we have a 0 to factor the polynomial. Okay, the only issue there, I mean, those two theorems are really great, but the hard part of the whole thing is to determine an actual 0, okay? And the way that we determined or tried to guess a 0 is to use the rational 0 theorem. And this is where we factored sort of the leading term and the constant term in our polynomial, and then we looked at all the possible ratios of plus or minus p over q, where p over q are the factors from the leading coefficient and the tail coefficient. And in many instances on the homework, you saw that that led to, you know, at least, you know, 10 or 12 different guesses. In the nice cases, there's, you know, only 3 or 4. But you should start just sort of plugging in those possible guesses to see if they're zeros with the simplest ones first. So we tried things like 0 or, you know, plus or minus 1, plus or minus 2, as opposed to something like 2/5 or 1/3 or something like that. That might be more difficult to deal with. So the rational 0 theorem was giving us potential zeros, but we still needed to plug them into the formula to show that they were indeed zeros. And when we identify that we have a 0, we can go through long division to get the factor x minus c that we multiply by this quotient to get back our f of x. Okay, and when we got this quotient, the degree of the quotient will be smaller than the degree of the dividend, right? The thing that we are dividing into, the f of x. And the process can then continue from there, right? That smaller degree polynomial, we can then again go through our process. If it's a quadratic, it's nice. We already have some methods for factoring it. But if it's not a quadratic, then you'll just have to go through the whole process again. And then I should mention that if you are very careful in those homework sections, you don't have to actually do long division. A lot of those questions could have been done by grouping by factoring. And if you can see that you can group it, do factoring by grouping, you can avoid some of the long division and using this rational 0 theorem. So that might be very helpful on an exam. Okay, and then, like I said, all of this information is useful for finding the zeros of our polynomial, right? So those 3 theorems you should be familiar with and ready to use on the final exam to be able to find the zeros of a polynomial. Okay, and then from there, we decided to move from polynomials to rational functions. And a rational function is just a ratio of 2 polynomials, polynomial on the top, polynomial on the bottom. And this is where we really started to use arrow notation pretty heavily, right? So we used the arrow notation to describe what was happening at vertical asymptotes and at horizontal asymptotes. So those were, you know, the vertical ones and the horizontal. The horizontal were much easier than the vertical because for the horizontal, you just had to look at the degrees of the 2 polynomials. If the degrees were the same, then you just look at the ratio of the 2 leading coefficients. If the degree on the bottom was bigger, then there's a horizontal asymptote at y equals 0. And if the degree is 1 more than the bottom, then there's a slant asymptote, and anything else means that there is no asymptote at all in the horizontal direction. On the other hand, for the vertical asymptotes, we first needed to find the domain of our rational functions. We found the domain by setting the denominator, the bottom of the fraction, equal to 0 using the factoring and the stuff from section 5.5 to identify the things that we had to remove from the domain, right? Because we can't let the denominator actually be equal to 0. So we had already done a lot of problems like this back in chapter 3 about finding the domain of rational functions. But the real difference here is that we now identified when those lead to vertical asymptotes. So if you factor the top and you factor the bottom and you see a common factor on the top and the bottom that leads to a 0, well, then we called that a removable discontinuity and there was no vertical asymptote. The vertical asymptotes correspond to zeros that don't have any corresponding factors in the top of the fraction that can be canceled out, right? So again, what you do is you factor the numerator, factor the denominator, cancel out as many common factors as you can. Those are the removable discontinuities. And then anything that's left over in the denominator that makes the denominator 0 is a vertical asymptote. And remember, asymptotes are lines, vertical or horizontal, and so you should write down the equation of those lines as something like x equals c for a vertical line, where c is a constant, or y is equal to c, where c is a constant for a horizontal line. And then all of this information was really useful in terms of figuring out the graphs of these rational functions. And it's sort of a two-way street there as well. So somebody could give you a graph and ask you to write down an equation. Basically, you want to look at it and see where all the vertical asymptotes are, the horizontal asymptotes. And then remember, we had to figure out the stretching factor, right? So the key piece there was getting an extra piece of the stretching factor. So that last objective there refers to both going from the rational function formula to the graph and from the graph back to the formula. So sort of both directions. And then last time we talked about 5.7 and we started to talk about inverses of polynomials. And what we realized was that not all polynomials were invertible. Not all of them passed the horizontal line test. So we needed to restrict the domain of many of them in order to actually find an inverse. So we talked about that in some detail. And then we saw that for certain polynomials, ones that passed the horizontal line test that were one-to-one, they were invertible, and often those invertible functions led to radical functions, right? So functions that had square roots or cube roots or things like this involved in them. So when you find the inverse of an invertible polynomial, you should probably expect there to be at least some radical in there, like a square root or something like this. And then remember that part of the domain restriction was also that when we were trying to do that process of finding the inverse, we might end up with a plus or minus from a square root, and the domain restriction will inform us on which one to keep, right? So that's what we were talking about in that final section on 5.7 and finding those inverses. And again, that's going to lead really nicely into chapter 6 because we'll introduce two new functions, the exponential and the logarithmic function, and they are naturally sort of inverses of one another. And then I guess the last thing that I want to say here about 5.7 is that if you have a function f of x, you know its domain and range, then you also know the domain and range of f inverse, right, the inverse function. And what happens is that the domain and range swap, okay? So the domain and range swap for the inverse. So keep that in mind as you're trying to compute the domain or range of the inverse of a polynomial function. Okay, so that's all I really wanted to say about chapter 5, just reminding you of the various pieces and how all of it sort of fit together, how long division and factoring fit together with the zeros and all of the graphs. Okay, so now that I've said that, I'm going to put up 5 questions on my Blackboard, and then I will end the video. And what I would like you guys to do is write down your answers to these 5 questions. You should include your supporting work, just like you would for the final exam. And then instead of doing this on Blackboard and Respondus, I'll just have you scan that in, that supporting work, and submit that as your quiz. Okay, so let's see what those questions are. So the first question we'll have on this quiz is related to finding the vertex of a polynomial. I'm sorry, of a quadratic. So here, your first question is find the vertex of f of x is equal to x squared plus 10x minus 7. Okay, so that's a minus 7. And again, the vertex is going to have an x value and a y value, and you need to find both, right? So it's an ordered pair. And you can think about it also as the turning point. And in this case, because the leading coefficient here is 1 and positive, this thing is opening upwards, and it'll be sort of at the bottom. It'll be a minimum. But nonetheless, this question is just asking you to find the location or the ordered pair that corresponds to the vertex of this function. Okay, so the next one is about multiplicities. So I would like you to identify the zeros first. And then their multiplicities. And in this case, I'm not going to give you a graph. I'm going to give you the formula. And I'm not even going to make you actually factor. I'm just going to give it to you in factor form. So it's going to be 3 times x minus 1 squared times x minus 2 cubed times x plus 1 to the 5th. Okay, and then just as a reminder, these exponents are there to help you determine what exactly the multiplicity is. Okay, so again, here we've got a nice vertex problem for a quadratic, and then we've got the zeros of a polynomial here that's already been factored, and trying to identify their multiplicities. And remember that when you find these multiplicities, they're telling you something about the graph, right? You identify the multiplicity, it tells you if you're sort of passing through the x-axis at that point, or if you're bouncing off of it. Either going, sort of hitting it from the top or hitting it from the bottom and going back down. Okay, so that is 1 and 2. And question number 3 includes a graph. So let me go ahead and erase these 2 questions. If you need to, you can pause the video and write them down. But the third question here is the following. So I would like you to identify the smallest possible degree of the following polynomial. And in this case, I'm going to give you the graph of this polynomial. And this is related to the relationship between degree and turning point. Okay? So here I'm just going to sort of not tell you anything about the labeling of the x and the y axis because it's not necessary. Again, all you really need to do to answer this question is think about the degree of the polynomial and the number of turning points. Okay, so that is question number 3. And just as a sort of quick reminder here of, this is not related to the question, but you have a 0 here, a 0 here, a 0 here, a 0 here, and a 0 here. And you'll notice that all of these have odd multiplicities because none of them are bouncing off of the x-axis. Okay, so again here we want to identify the smallest possible degree. There may be many polynomials that have this particular shape to them, but there are some with the smallest possible degree. Okay, so that's number 3. Number 4 is going to be about dividing things. So you'll get a little bit of practice with some long division for this question. This is question number 4. And again, all of these are really good practice for the upcoming final exam. So for this one, let's look at dividing x cubed plus x squared plus 7x minus 3 by the factor x minus 7. And here I'll specifically ask you to identify the quotient and the remainder. So on an exam, if they ask you this sort of thing, identify the quotient and the remainder, you should clearly label what you think the quotient is and clearly label what you think the remainder is, right? So here, this is our dividend, this is our divisor. We'll get some remainder at the very bottom, and that thing that goes on the top of that division bar is going to be what we call the quotient. Okay, so this is another really good example of something that you might end up seeing, for example, on a final exam. Okay, and then in the final section, we talked about inverses, and in particular inverses of rational functions. So I'll give you one with some difficult algebra, right? And there was one almost identical to this on the midterm exam, but here we're going to ask you to sort of do this again because, again, a lot of people really miss the algebra on that particular set, or that particular question. So here we're going to find the inverse of the following function. F of x is equal to x plus 1 divided by x minus 2. And we should already sort of see, what the graph might look like here. We're going to have a horizontal asymptote at 1 because the degrees on the top and bottom are the same, and the leading coefficients are 1 and 1. There's going to be a vertical asymptote at x equals 2 because that's where the denominator is equal to 0. There's going to be an x-intercept at -1, 0, and that's because if I set this top piece equal to 0, I can solve for x and get x is equal to -1. Okay, so as a reminder here, how do we find the inverse? Well, we replace f of x with y, we swap the x's and the y's, and then we solve for y. And the hard part about this question is really the solving for y. We'll need to use the distributive law at some point. And then after you do that, you should state the domain and the range of the inverse. Okay, so not the function f of x, but its inverse. Okay, and those are the 5 questions that I will ask you to complete for the quiz this week. Again, there won't be any quiz on Respondus lockdown, just on the video here. Thank you guys, and have a nice day.